Hello and welcome back to geometry. Today we will be looking at section 4.7, which deals with vertical angle. So in this section, we're going to go ahead and define what is a vertical angle and also proving a theorem called the vertical angle theorem, which it will be definitely very, very useful from here on out. So here we go. Let's go ahead and get started. First, we're going to go ahead and define what is a vertical angle. So as you can see, there's a picture on the right-hand side where you have two lines that are intersecting each other, AB and DC. Their intersection is going to be some point P. Now, just to make it a little bit simple, I'm going to go ahead and name each of the angles 1, 2, 3, and 4, just so that I don't have to write out the whole thing. And you can always do that in a proof also, just to make things a little bit shorter too. So anyhow, two angles are considered vertical angles if their sides are opposite rays. So here you can see that what I'm pointing at is that here, number 2 right here, this angle 2, BPC if you want to call it that way, and also angle 4, DPA right there, those are considered vertical angles because you can see that the sides that makes up those angles, they basically form opposite rays then. So that's going to be the set of the pair of vertical angles. And by the way, vertical angles always comes in pairs because there are always going to be two of them. Okay, and similarly, I can say that 1 and 3 are also vertical angles because once again, DPB and also APC, those two angles, if you look at their sides, they form opposite rays as well. If you haven't noticed already, maybe we can go a little bit further with that. These vertical angles, they are congruent to each other. So that is to say that angle 1 is the same as angle 3, and angle 4 is considered the same as angle 2. Well, we're going to go ahead and do a proof of that, and that's what this theorem 4.8, also known as the vertical angle theorem, is about. So in here, we're given that these two lines are just going to intersect each other at some point P, and that's really all we're given. Not a lot to work with. But in the end, what I want to do is I want to prove that 4 is congruent to 2, and also 1 is congruent to 3. Or in the end, we can also say the measurement of angle 4 is equal to the measurement of angle 2, or measurement of angle 1 is equal to a measurement of angle 3. Just to make this theorem a little bit more versatile, instead of like just saying that you only can use it if it's congruent, or you can only use it when it's equal to each other. You can use it for either one. All right, so here we go. So we kind of did this last time, but if you didn't remember it, let's go ahead and get started. Here in the step 1, now this is the 1% of the time that, like I said, your beginning statement and reason, your reason is not going to be a given, but instead it's going to start as angle 1 and angle 4 are going to form a linear pair. So pointing that out, that's saying these two right here, they're going to form a linear pair because you can see that they're on the same line. Note that again, that's not one of the given, but I think that's what we can work with. You can't really do too much with AB intersection with CD is equal to point P because that's well, there's nothing much to play with over there. And then what I'm going to say is also angle 2 and angle 1, they're also going to form a linear pair. So you can see it over here. Angle 2 and angle 1, they're going to form a linear pair. Angle 4 and angle 1 is going to also form a linear pair. Now, why did I specifically choose those two? Well, it's because they both have 1 in common. I technically could choose a different combination, but we're just going to go ahead and stick with this one for right now. So going through the procedure, once we say that they are a linear pair, then we can go ahead and say that they are supplement to each other because of the supplement postulate, which is also known as postulate number 14. So it's probably better just to say the supplement postulate then, not definition of supplementary, which is the next thing actually. Step 3, once we say that they are supplement to each other, then we can say by the definition of supplementary, the measurement of angle 1 plus the measurement of angle 4 is equal to 180 degrees. And finally, 180 degrees is also equal to measurement of angle 1 plus the measurement of angle 2. Well, now that we know that they're both equal to 180 degrees, we can go ahead and set them equal to each other. And that's going to be step 4 over here to say that measurement of 1 plus 4 is equal to the measurement of 1 plus 2 then. And that's just a transitive property. Note again how they're related to each other by the measurement of angle 1. So because angle 1 is on both sides, we can go ahead and subtract from both sides. And so now we end up with what we were trying to show to begin with, which was the measurement of angle 4 is equal to the measurement of angle 2. And like I said, just to go ahead and reiterate a little bit further, we're going to go ahead and say that they are congruent to each other in step 6, just so that next time when we use this theorem, we can now expand to not just having congruence, but also having to use it when you have the measurements are equal to each other. If you want to do the same thing for 1 and 3, you can probably do that. Maybe what we can do is say that 1 and 2 are going to be a linear pair, and 2 and 3 are going to be a linear pair, and we can go through that same procedure and get exactly the same thing, just showing that 1 is now equal to 3, or congruent to 3. All right, but anyhow, let's go ahead and deal with this theorem in this section, which is a very minor one, but it's worth mentioning because there are some times that something like this pops up and we actually want to use this just to make things a little bit easier. Here we go. And by the way, also this we have to use the vertical angle theorem in this theorem too, because if we're proving something, we might as well try to use it as well, right? So that's where this is going to come in. All right, so anyhow, theorem 4.9, it says that if two lines are perpendicular to each other, okay, if two lines are perpendicular to each other, then they form 4 right angles. Well, here, what I know is that L1 and L2 are perpendicular to each other. That's all I have to work with. What I need to show is a proving part right here, just to write it as an if and then statement. I want to prove that these guys right here, angle 2, angle 3, and angle 4, are also right angles. I guess also technically angle 1 is also a right angle too. So I need to prove that all 4 are right angles then. So let's go ahead and see what we can deal with, okay? In the first part, we can only work with the fact that those two lines are perpendicular to each other. So right there, you can see that is going to be my given then. So they are perpendicular to each other. Next, if we know that they're perpendicular to each other, then that means that there is a right angle, and that's the definition of perpendicular. This was a while back when we say that when a line is perpendicular to another line, or if a ray is perpendicular to another ray, or if a segment is perpendicular to another segment, or any variation of that sense, you're going to form a right angle as a result. So right there, we snuck in one right angle. Now we're 1/4 of the way done because we have to prove the other 3 angles are going to be right also. So next, what we can do is we can pull out of thin air that same thing as what we did in the previous problem. And that's basically say that let angle 1 and angle 2, say that angle 1 and angle 2 are going to be linear pairs. So you can see that they are all on that straight line of line 1. So that's why we can do that. Can I say some other ones? Yeah, definitely. So I'm just going to choose one of them for right now. Okay. And then now, if you notice, we're just going through the same procedure as last time. Right? To say that they are linear pair, then allows me to say that they are supplement because of the supplement theorem. And then from the supplement, we can say that they are equal to 180 degrees because of the definition of supplementary. So now you can go ahead and take those two information, because I see step 1 and step 2 is kind of like, okay, that's as far as you can go. And then step 3 and 4 and 5, that's like another subset of this proof, and that's as far as you can go. Now we take what we have over here and what we have over here and try to combine it together. Go back. Remember, we said that step 2, angle 1 is a right angle. So we can go ahead and further expand that in step 6 to say that it is 90 degrees. Could we have done that in between step 2 and step 3? The answer is yes. If you wanted to put it there, I think that might be useful too. But I put it next to step 5 and step 6 because now what we can do is we can say, hey, since measurement of angle 1 is 90, and the measurement of angle 1 plus 2 is equal to 180, we can go ahead and make a direct substitution for 90 degrees for measurement of angle 1. So that's where the substitution is coming in. So I usually like to write the proof, usually like to write the statements when they are necessary, not when they are convenient for me. Okay. So now that we took step 5 and step 6, combined it together to get a substitution, and here I can go ahead and do that, and we can say that's from step 5 and step 6. Now we can take that equation and clean it up a little bit by subtracting both sides by 90 by the subtraction property of equality. So that gives me the measurement of angle 2 is equal to 90 degrees. And then by formal definition of right angle, then we can say that angle 2 is a right angle. So from there, from what I have right now, is that I proved angle 1 is a right angle. So that part is done. I also just proved in my proof that angle 2 is a right angle. So that part is done. Now let's think about angle 3 and angle 4. Well, how about let's think about the vertical angle theorem also, just what we proved earlier. Angle 1 and angle 3, according to the vertical angle theorem, should be equal to each other, should be congruent. Well, if there are right angles in one of them, then the other one definitely should be a right angle. And similarly, angle 2 and angle 4, they are vertical angle as well. So that means that if 2 is a right angle, then 4 is a right angle. So let's go ahead and continue and finish our proof for this one then. Here's basically what I just said. Angle 1 is congruent to angle 3 because of the vertical angle theorem. Or you can say measurement of 1 is equal to the measurement of 3. Either one should be okay. And finally, for the last one, measurement of angle 2 is congruent to measurement of angle 4. Angle 2 is congruent to angle 4, not the measurements. And then now we can go ahead and say that 3 and 4 are right angles because they are both congruent to their respective counterparts, which are 1 and 2. So any two right angles are congruent to each other. So notice how in step 10 I used the vertical angle theorem, what we proved earlier. So that's what we want to try to do now. We're going to try to use all the previous proofs to help us build into bigger and more complex proof. All right, thank you so much for watching. I will see you.